So yes, hello everyone. Thank you very much to the organizers for inviting me. Special thanks to Matt, and thanks everybody for coming to my talk. I was so much looking forward to this visit, to meeting everybody, but unfortunately life is not as we plan it. And due to some health problems, I couldn't make the trip, but still I'm happy to give this Zoom talk. So I'll share my screen. Okay. So this talk will be about combinatorics and quantum K-theory Schubert calculus. So the story of combinatorics in Schubert calculus, as you well known, is very old one, and most of the time we use combinatorics to perform explicit calculations in Schubert calculus on flag manifolds. But the message of my talk related to quantum K-theory Schubert calculus now, the main message will be that combinatorics actually can do more. Combinatorics sometimes can get ahead of the geometry and can offer good intuition and can guide the geometry. This talk is basically a survey of work that I've done over the years in this area, and it's mostly work with my long-term collaborators Satoshi Naito and Daisuke Sadaki, and also with several other collaborators, which I will mention. So let me get started, and feel free to interrupt me and ask questions whenever needed. So the plan of the talk is the following. So I'll give some background on equivariant K-theory and equivariant quantum K-theory of flag manifolds G mod B. Then I'll discuss the combinatorial model that I mentioned in my abstract called the quantum alcove model. Then I'll show you how we can use this model to express an important multiplication formula called the Chevalley formula in the equivariant quantum K-theory of flag manifolds G mod B. And then there will be several applications of this formula and related results. And finally, a more recent result, which we just finished proving with my collaborators and Weyl as well, is this conjecture of Anders Buch and Leonardo Mihalcea on the quantum equal classical phenomenon in K-theory. And then I will also discuss some follow-up. So to fix the notation, G is a semisimple Lie group over the complex numbers. We have the maximal torus, the Borel subgroup inside. All my examples will be type A, so G is SLN and B is upper triangular matrices in SLN. Then we have the simple roots alpha I, the simple core roots. The indexing set for the Dinkin diagram nodes is capital I as usual. In type A, the roots are differences of coordinate vectors, epsilon I minus epsilon j. And I will also denote them with pairs, just with a pair I comma j. And then we have the simple roots. The fundamental weights will be denoted omega I, and their z-span forms the weight lattice. In type A, the omega I are just the sum epsilon 1 plus epsilon I. And then we consider the group algebra of the weight lattice, which is the representation ring of the torus, and it's the z-span of these formal exponentials x to the lambda, or weights lambda. And W is the finite Weyl group, SI the simple reflections. So in type A, it's the symmetric group, and reflections are transpositions, and simple reflections are adjacent transpositions. So then when we look at, so I think there were some talks, I think Dave Anderson gave a talk on K-theory. So when we look at the equivariant, T-equivariant K-theory of the flag manifold G mod B, we consider it over as a module over the K-theory of a point, which is the group algebra of the weight lattice. And we consider the following bases. So we have the Schubert classes indexed by Weyl group elements, OW, which are classes of structure sheaves of Schubert varieties defined in the usual way. Then we also have the opposite Schubert classes, O upper W, for the opposite Schubert varieties. And then we also have the duals to the latter, denoted O sub W check, the dual with respect to the K-theory pairing. And then a Chevalley formula is just a multiplication formula of an arbitrary Schubert class with a divisor class, so one indexed by a simple reflection. So we expand in the basis of Schubert classes, and we get these equivariant coefficients x to the mu, and then some integers, c, w, v, mu. Sometimes Chevalley formula is formula with multiplication with the class of a line bundle. But the two are basically the same. So here I will just consider multiplication with the divisor class. And there is a similar version for the opposite Schubert classes. And with Postnikov, many years ago, we gave a combinatorial Chevalley formula for K-theory in terms of what we call the alcove model. And then with Shimozono, we generalized the alcove model to symmetrizable Kac-Moody algebras, so to infinite root systems. And we gave a corresponding Chevalley formula for Kashiwara's thick flag manifold. So now we consider quantum K-theory of G mod B as defined by Giventhal and Lee. So it's usually defined for a projective manifold X as a K-theory version of quantum cohomology. So just very briefly how we define it. We consider a degree D, so just a sequence D1, dr of positive integers, non-negative integers. Sometimes you think of it as the corresponding linear combination of the simple coroots. And a triple of Weyl group elements, U, V, W. And then one defines this K-theoretic Gromov-Witten invariant, denoted like this, O, U, O, V, O, W check of degree D. So it's called 3-point equivariant degree D KGW invariant. How to define it? Basically, so first recall that in quantum cohomology, we have the usual Gromov-Witten invariants, and they count curves of degree D, which pass through the respective Schubert varieties. And these are actually the structure constants for quantum cohomology. For K-theory, sometimes this space of curves is infinite, and then one gets a number, this KGW invariant, by taking a K-theory Euler characteristic of this space of curves. So I don't want to give precise definitions. It would take me too much. But just roughly, this is the story. And actually, there is more. Then we consider the coefficient ring by introducing quantum parameters Qi, so the polynomial ring in the Qi's, and we combine it with the group algebra of the weight lattice. So this will be the coefficient ring for T-equivariant quantum K-theory of G mod B. And then this algebra is actually defined as a module is precisely the tensor product of the usual equivariant K-theory with this quantum coefficient ring. And when we set the Qi's to 0, we just recover usual K-theory. So now we will consider this algebra with the basis of structure sheaves of opposite Schubert varieties, these O upper W. And how to define their multiplication? Well, we define the multiplication by defining the structure constants not as the KGW invariants like we do in quantum cohomology, but by plugging these KGW invariants in some recursive formula, actually the 2 and the 3-point invariants, we plug them into a recursive formula, and this is how the structure constants come out. And magically, we get an associative algebra. And that's the quantum K-theory algebra. The product will be denoted with a star. So then, again, we look at Chevalley formula, so multiplication by the class indexed by a simple reflection with an arbitrary class. And for this, we'll give a combinatorial formula with my collaborators, Naito and Sagat. So now I will have to tell you about the combinatorial model, this quantum alcove model. So this is based on Weyl group combinatorics. So the basic structure is the Weyl group, but on the Weyl group, we consider the covers of the Bruchau order. So we have an arrow from an element W to W multiplied by an arbitrary reflection, edge labeled alpha, whenever the length increases by 1. But to these covers, we also have to add so-called quantum edges, which are downward edges. And we have such an edge whenever the length decreases by a lot. And a lot means twice the height of the core root alpha minus 1. And the height is just defined by expressing in the basis of simple core roots and adding up the coefficients. And this structure originates in the quantum cohomology of flat varieties as defined in the corresponding formula given by Fulton and Woodward. So for S3, for the symmetric group S3, here we have the covers of the Bruchau order. We have the permutation, the identity at the bottom, length 0, and the longest permutation at the top, and the covers of the Bruchau order with the respective labels. And then we add these downward edges. So for instance, if you take the longest permutation, 3 to 1, you exchange 1 and 3, you get the length 0, 1, and that's a large drop. So you have an edge in the quantum Bruchau graph. And now we'll consider paths in the quantum Bruchau graph. Paths with some start and some end. And the quantum edges with the covers can alternate in any order. And then we have this, we look at the places where we have down steps. So quantum steps in this path. That's down of P. And then the quantum weight of the path is just obtained by summing the labels, the core roots actually, corresponding to the edges where you have down steps. That's the quantum weight of a path. And Postnikov proved that if you take all the shortest paths between two Weyl group elements, then they all happen to have the same quantum weight, and this will be denoted by quantum weight from W to V. So this will be a result we'll need. So then the quantum alcove model, I can explain it now. Its main feature is that it's uniform for all root systems, and it's just based on combinatorics of the Weyl group W. You also have to input a certain weight, let's say arbitrary weight lambda, and with it we associate a sequence of roots called the lambda chain. So beta 1, beta m are roots, positive or negative. This encodes actually a shortest sequence of adjacent alcoves from connecting the fundamental one to the translated one by negative lambda. And it actually comes from a factorization of the translation element in the affine Weyl group. And explicit constructions are available. And the model is actually independent of this choice of a lambda chain. We'll discuss this more, but you have to fix such a choice at the beginning. So here's in type A2, if you consider the weight 3 epsilon 1 plus epsilon 2. So here in red, you have the positive roots. In blue, you have the coordinate vectors, which sum to 0 because you have to quotient by the sum of epsilon 1 plus epsilon n. And then in red, you have the positive roots. And orthogonal to them, you have the reflecting hyperplanes. And then you also consider translates of them to get the alcove picture. And then the shaded alcove at the top is centered, I mean, with one vertex at the origin is the fundamental alcove, and the one here at the bottom is the translated one. And then you see here a blue path connecting the two, and you simply record all the hyperplanes that are crossed in this process. So you basically look at the roots that are orthogonal to all of these 6 hyperplanes that are crossed. So the roots are listed here at the top. Epsilon 1 minus epsilon 2 is the orthogonal to the first hyperplane that's crossed, and then you have 1, 3, 2, 3, 1, 3, 1, 2, 1, 3. 1, 3 is the last one. So you record this the sequence, and that's what I call a lambda chain. Very important for this talk will be chains of roots for the negatives of the fundamental weights. So in type A, such a chain is given by this matrix, read from left to right and top to bottom. So ij are the roots epsilon I minus epsilon j, and you notice here that the last root is always the simple root alpha I. So epsilon I minus epsilon I plus 1. That's the last root in this chain of roots. And that's true for any root system. So now if you fix such a chain of roots, then you record the Rj will be the reflection corresponding to the jth root. But there will be also an affine reflection here, Rj hat, because remember, these hyperplanes that are crossed are affine hyperplanes. So you just simply look at the affine reflection corresponding to the jth hyperplane. So this is Rj hat. So then the objects of the model are just subsets of these positions from 1 to n. Let's call them J1 through Js, increasingly. And then you also have to fix some Weyl group element W. And given these positions J1 through Js, you start from this W, and you build a chain of Weyl group elements by multiplying on the right, one by one, by the reflections corresponding to the positions J1, Js. So you multiply W, Rj1, Rj2, Rjk. Eventually, you multiply by all the reflections corresponding to these positions, non-affine reflections. So you have the start of the path and the end of the path. And then the condition that you want to put on how to choose these subsets is that the path that corresponds to the subset, this path has to be a path in the quantum Bruhat graph. So just a random path in the quantum Bruhat graph. So this notation QBG W gamma will be all the so-called admissible paths which start at W and are based on the lambda chain gamma. So admissible means that the path is in the quantum Bruhat graph. And we also associate, so we have a quantum weight for any path in the quantum Bruhat graph that will be needed, but we also have a usual weight. So that's just computed like indicated here. So you just apply these affine reflections to negative lambda, then you apply W, and you change the sign at the end. So going back to my running example, if in this chain of roots, if you pick the third root and the sixth root, the last one, and if your starting permutation is 3, 1, 2, then you get an admissible quantum Bruhat path, because if you switch entries 2 and 3, that takes you up in length by 1, so that's admissible. And then you get to the longest permutation, and when you switch 1 and 3, it gets you to the identity, and that's the large drop in length. And that's also an edge of the quantum Bruhat graph. But when you start from 3 to 1, and you apply the same transpositions, then the second edge from 3, 1, 2 to 2, 1, 3, it's a downward edge, and it's not an edge of the quantum Bruhat graph. So this will not be an admissible path. So now I can finally explain the Chevalley formula. So we remember we have to fix a degree. So positive integer combination of the simple core roots. And then there will be a monomial in the quantum parameters associated with it. So this will simply be Q1 to the D1, QR to the DR. R is the rank of the root system. And then I can state the Chevalley formula, which we proved with Naito and Sagaki. Actually, we conjectured it with Postnikov in 2007 because it was just a natural generalization of the formula, Chevalley formula we gave for ordinary K-theory. So we fix a node I, or a simple reflection if you want. And then we have to fix negative omega I chain of roots, which we denote gamma I. And I already showed you how this can be chosen explicitly in type A. But I have explicit constructions in all the other classical types, and actually an algorithm to find such a chain of roots in general. And then the Chevalley formula is quite easy to write down. So if you want to do the quantum multiplication of the divisor class indexed by SI with some arbitrary Schubert class, you expand in the basis of Schubert classes. Then first you get again the Schubert class indexed by W with this equivariant coefficient. And then you get a sum over all admissible quantum Bruja path starting at W, which are based on the chain of roots gamma I, except for the empty path. And then you have a sign, which is the length of the path, -1 to the length of the path -1. Then you have a Q monomial, a monomial in the quantum parameters. And this is given by the Q weight of the path. Of course, you have to express this in the basis of the simple core roots, and then here is the definition of Q to some element of the root lattice. And then the equivariant parameters are given by the weight of the path, minus omega I minus the weight. And these are all the coefficients for the Schubert class indexed by the end of the path. So for each path, you look at the last element in the path. So that's the Chevalley formula. And there is a little bit of history related to it, which is actually quite interesting, where this comes from. It has to do with a semi-infinite flag manifold denoted QG. This is an affine version of a non-standard, I would say, affine version of the usual flag manifold G mod B. There is the usual affine flag manifold, but this is not that one. It's another version, non-standard, called the semi-infinite. And then this quantum alcove model was first developed in connection with the representation theory of certain modules of affine algebras called level 0 extremal weight modules. So here the abbreviations are indicated here at the bottom. So with Naito, Sagaki, Schilling, and Shimozono, we use the quantum alcove model to give character formulas, but not just that, but to express the crystal structure of these modules. So the crystals are somehow recording some information about the representation, enough information to allow you to do the basic computations in representation theory. And then Kato, Naito, and Sagaki were able to relate these modules to the K-theory, equivariant K-theory of the semi-infinite flag manifold. And they used Borel of some affine version of the Borel-Weyl theorem that they proved to relate these modules, to construct these modules in the space of certain line bundles on the semi-infinite flag manifold. And then Kato had a further breakthrough by relating the K-theory of the semi-infinite flag manifold to the quantum K-theory of the usual flag manifold. So this is a phenomenon known as quantum equals affine. So you have the quantum K-theory and the K-theory of this affine flag manifold. And the quantum alcove model allows you to do computations in all of these areas. So this result of Kato, I'll just mention it briefly. It was a subject of an ICM talk in 2022. Kato said that there is this Z of P module isomorphism between the equivariant quantum K-theory of the ordinary flag manifold and this subring of the K-theory of the semi-infinite flag manifold. And this is just a K-theory version of a similar quantum equals affine phenomenon in quantum cohomology that's known as the Peterson isomorphism. And the K-theory version was also there were some previous results. It was foreseen by other people, and it was also developed in a paper by Chow and Leong more recently. So that's the story. So that's the story of the Chevalley formula. And now I want to show you many applications, many ramifications that follow from here, many additional results that are made possible by this formula, including the proof of some longstanding conjectures. So first, I'll briefly discuss some combinatorics of the quantum alcove model. Then I'll show you how you can use the Chevalley formula for G mod B to derive Chevalley formulas for partial flag manifolds. And then we'll get more specific results in type A, which tell us more about the structure of the quantum K-theory of the type A flag manifold. And then I'll end with this more recent result, which is this proof of a conjecture of Anders and Leonardo, known as the quantum equals classical phenomenon. So for the combinatorics of the quantum alcove model, the basic thing is to show the independence of a model from the choice of a lambda chain that I mentioned at the beginning. So remember, the model depends on some chain of roots for the weight lambda, on some Weyl group element W, which gives you the starts of all these paths in the quantum graph. And then we have these statistics for paths, the weight, the end of the path, and the quantum weight. And we look at the set of W admissible paths starting at W based on gamma. And we take the generating function of these statistics over this set that we need to consider for the Chevalley formula. And then we proved, part of our paper was to prove that this generating function is independent of a lambda chain. So if you have two of them, shortest corresponding to two shortest alcove paths, then the generating functions are the same. So we know this, but it would be nice to realize this combinatorially. Presumably there should be some bijection between the paths for gamma 1 and the paths for gamma 2, which preserve the statistic. But it's interesting, it's not quite a bijection. So the combinatorial realization was done in a paper with Kouno, student of Naito. So first, we assume that gamma 1 and gamma 2 are pretty close. So they are related by an elementary transformation known as a Yang-Baxter transformation. This just takes some subsequence of consecutive positive roots in some lambda chain, which form the roots of a rank 2 root system. And we simply reverse this. So it basically corresponds to applying a Coxeter move on a reduced factorization of the translation element by the corresponding weight. So if gamma 1 and gamma 2 are related by the reversal of such a sequence of roots for a rank 2 root system, then the corresponding admissible paths for gamma 1 and gamma 2 do not necessarily have the same cardinality. But we can construct what's called a sijection between them. So sijection is a bijection between sign sets. Because these paths, they remember in the Chevalley formula, they come with a sign, which is -1 to the length of the path. So these really are sign sets with signs. And then we construct the sijection between them, which preserves the statistics. And that's enough to show that the generating functions are the same. And such a sijection is called a quantum Yang-Baxter move. And then we simply apply it repeatedly because one can show that repeated applications of such Yang-Baxter transformations can relate any lambda chain to any other one. So this is how you explicitly realize the equality of the two generating functions. You realize it combinatorial. Then I said that another issue is now to derive Chevalley formulas for partial flag manifolds. So if we consider a subset J of the nodes of the Dingin diagram, Pj is the corresponding parabolic subgroup. And with Kouno, Naito, and Sagaki, we gave cancellation-free formulas, cancellation-free Chevalley formulas for the quantum K-theory of G mod Pj in the following cases. So the key here is this cancellation-free, because we can get easily some formula, but it's important to be cancellation-free. And our original Chevalley formula for G mod B, as I said, is cancellation-free. So we derive such cancellation-free formulas in type A, B, D, and E for maximal parabolics when we exclude a minuscule node, omega k. A minuscule node k, so the weight omega k, the fundamental weight omega k, is minuscule. And this is a different formula than the one given by Buch-Mihalcea, Mihalcea, and Perrin. But I think at this point there are bijections between the two formulas. Then in type C, we can do more than minuscule case. We can do actually any node or a maximal parabolic. And in type A, we can go beyond the Grassmannians, the maximal parabolics, by looking at two-step flag manifolds. So we exclude two nodes, K1 and K2. And in all these cases, we gave cancellation-free formulas. And the idea is pretty simple. So we start with the Chevalley formula for the full flag manifold G mod B. And then we apply another important result of Kato, which is a module surjection over the group algebra of the weight lattice from the quantum K-theory of G mod B to the quantum K-theory of G mod Pj. So that's quite surprising that there is such a module surjection preserving products. But then we get the Chevalley formula in the partial flag manifold case, but it will have cancellations. And then the task is to perform all these cancellations to construct some clever sign reversing evolution, and then you end up with cancellation-free form. And then we have some additional results for type A. So here we just look at quantum K-theory of FLN. So FLN is SLN mod B, or the variety of complete flags in C to the N. So we look at the Chevalley formula. So this should have been star here. Dot is reserved for the K-theory product. So here is the quantum product of Schubert class indexed by a simple reflection and an arbitrary Schubert class. And we look at the coefficient of a class indexed by V times this quantum monomial. And this is non-equivariant for the moment. And this coefficient I call NSKWV upper D. D is this degree. So also as part of our paper with Naito and Sagaki, we showed that all these QK Chevalley coefficients are plus minus 1 or 0, and they are explicitly described. That's not the case in other types, but in type A, this always happens. So then we can go a bit further. So a long time ago with Maeno, we constructed, we want to get a presentation now for the quantum K-theory ring. So to get a presentation, we have to define these quantum elementary symmetric polynomials. So these are polynomials in X and also the quantum parameters Q, such that when we specialize the Q's to 0, we get the usual elementary symmetric polynomials of degree P in the variables x1, xk. So that's a complicated definition. And I will also use a version with a bar, which just comes by setting the last quantum parameter Qn to 0. So then there was an old conjecture of Kirillov-Maeno about the presentation of the quantum K-theory of the type A flag variety as being the quotient of this polynomial ring in X and Q by the ideal generated by these elementary symmetric polynomials E1 and ENN, and we use the version with the bars. So this now was proved also based on the Chevalley formula. So as I said, the Chevalley formula allows us to derive lots of other interesting results. And then Maeno, Naito, Sagaki went further and extended the presentation to the T-equivariant quantum K-theory of the type A flag variety. And they used slightly different methods. And then there was another step further done very recently by these people indicated here, where they derive now the presentation for any type A partial flag variety. Okay. Now, going back to these quantum elementary monomials, one can play a game that Fomin, Gelfand, and Postnikov played for quantum cohomology. One takes these elementary monomials, some monomials in the elementary symmetric polynomials, and sends this monomial to the same monomial, but in the quantum elementary symmetric polynomials. So we define this quantization map, and so following the recipe of Fomin, Gelfand, and Postnikov, which led to the definition of quantum Schubert polynomials, with Maeno we define these quantum Grothendieck polynomials by simply taking the usual Grothendieck polynomials of Lascaux and Schützenberger and taking their image under the quantization map. So there are some polynomials in Q and variables X for any permutation W in Sn. Remember that the usual Grothendieck polynomials are representatives for the Schubert classes in ordinary K-theory of the type A flag manifold. So then, of course, one wonders about quantum K-theory, whether we have a similar result. And we had an indication that might be true because with Maeno, we proved that the quantum Grothendieck polynomials satisfy what at that time we conjectured to be a Chevalley formula for quantum K-theory of the ordinary flag manifold. But now this Chevalley formula is proved, and then simply as a corollary, we get that the quantum Grothendieck polynomials represent Schubert classes in quantum K-theory. So this we conjectured with Maeno in 2006, but we could only prove it once we have the Chevalley formula in quantum K-theory of the ordinary flag manifold. So therefore, we can use these polynomials to compute structure constants, any structure constants we want. So we take any two such polynomials, multiply them, expand in the basis of these polynomials, and look at the coefficients. Of course, this you can do on a computer, but we only have a rule so far in the Chevalley case, but I will also say a bit more. We can actually do a bit more. But in principle, we can compute any quantum product. So we solve this, this conjecture that I had with Maeno. So this was now extended to T-equivariant quantum K-theory of the type A flag manifold by Maeno, Naito, Sagaki, published in 2025. And now they used the quantum double Grothendieck polynomials, which we also defined with Maeno in 2006. Okay, and this brings me to my last application of the Chevalley formula, which is this quantum equals classical phenomenon. So this happens when a cohomology or a K-theory, a Gromov-Witten invariant, equals a classical or a degree 0 invariant. So this was proved by Buch, Kresch, and Tambakis in several instances for a quantum cohomology. And in quantum K-theory, there is a general conjecture of Buch and Mihalcea for Gromov-Witten invariants of Chevalley type. So one of the three classes in the 3-point KGW invariant is a class indexed by a simple reflection. So this result can be thought as a replacement for the so-called divisor axiom in quantum K-theory. And this conjecture was only proved in very special cases. So let me state the conjecture, and then I'll discuss its proof, and we'll see how the Chevalley formula can really help us prove this. So if you consider two classes in T-equivariant K-theory, a simple reflection Si and a degree D, then the equivariant 3-point KGW invariant involving the class indexed by a simple reflection and the other two random classes is the conjecture said it should equal to a 2-point invariant, but there are two cases, whether the ith component of the degree is bigger than 0 or if it's equal to 0. And if it's equal to 0, then you have this 2-point invariant, which involves the product in K-theory. So here you will have the Chevalley formula in K-theory multiply some arbitrary class with Schubert class indexed by a simple reflection. So this conjecture really says that the quantum invariant is equal to a classical one if you take these dual bases, the opposite Schubert classes and its dual bases. But we tried to prove the theorem for a long time using this pair of bases, but it was very hard because it involved the notion of curved neighborhoods and Hecke product, and it became very, very hard. But then the breakthrough came very recently when we realized that it's much easier if you use the opposite Schubert class and you pair it with the usual Schubert classes. And for simplicity here, we restrict to the non-equivariant case and to minuscule nodes for simply laced root systems. So the quantum equals classical conjecture is related to the QK-Chevalley formula because the QK-Chevalley coefficients are related to the respective KGW invariants via a formula which I mentioned at the very beginning due to Giventhal. So I'll write it explicitly here. So this 3-point KGW invariant is a sum of these Chevalley coefficients that I defined earlier times a 2-point invariant of degree E. So it's a sum over the Weyl group element and all degrees less or equal to D. So less or equal, it's component-wise comparison. And then we have to combine this with a result by these people, which gives you these 2-point invariants are 1 or 0, and the deciding factor involves this quantum weight of the paths that go from W to V, which was defined earlier. This quantity that doesn't depend on the path, as long as it's the shortest path. So the key idea is to use the Chevalley formula to express these Chevalley coefficients, quantum K Chevalley coefficients, in terms of these quantum Bruhat paths, and combine that with these 2-point invariants being 1 or 0, and then we rewrite this formula to prove in a much simpler and combinatorial way. Remember that we have to, for the Chevalley formula, we have to choose a minus omega I chain of roots. We do that. And then we have to look at the subset of the admissible paths that start at U and are based on this chain of roots gamma I. So we select the subset of paths here by some conditions which don't matter very much. They involve the quantum weight of paths. So we have this selection of a subset of paths. And then this really comes from the key idea that I explained before, just using the Chevalley formula, combining it with the Giventhal's formula. And then Giventhal's formula can be rewritten combinatorially as simply these that this 3-point invariant is equal to this the sum of plus minus 1 plus the 2-point invariant. And then the Buch-Mihalcea conjecture, in the case di equals 0, based on this equality, is very easy to prove. The case di bigger than 0 is a little bit more interesting. So in that case, we have to prove that this 3-point invariant on the left-hand side is equal to the 2-point invariant on the right-hand side, which would simply say that this sum here should be 0. So the conjecture just amounts to showing that this sum is 0. So what we need is a sign reversing involution on these quantum Bruhat paths. So a subset of Bruhat paths starting at U based on gamma I. So we need to prove this. And there is a simple idea for constructing such a sign reversing involution. Remember, in this chain of roots gamma I, the simple root alpha I is always the last one. So now the simplest idea is to just say that if you have a path in this set, you just look if the last step of this path involves the step, the edge labeled alpha I. If it doesn't involve it, you add it. If that edge is there, you remove it. So that's clearly an involution. And an edge labeled alpha I is always an edge of the quantum Bruhat graph. That's a well-known fact. So we are fine. The only complication is that sometimes this theta of P obtained by removing or adding the last step is not in the set you want. So then the involution needs to be adjusted. And then you get into a little bit of discussions of cases, but that's doable. And you can handle that. And then this approach extends to the T-equivariant case. It extends to some nodes in the non-simply laced types, not just the co-minuscule ones. And it actually extends to all types and all nodes, but then you need a certain combinatorial correction term in the conjecture formula. So the formula is not true in full generality for all nodes, but we can control the correction. And one can do also the case of partial flat varieties with the same method. But in addition, Leonardo and Wei Hong derive the G mod P case from the G mod B one. So that's another route. So now let me show you when the conjecture holds as stated. So this can be described using the highest root of the corresponding root system and theta check is the corresponding core root. So then the theorem is that the conjecture holds as stated, that this 3-point invariant is equal either to the first 2-point invariant or the second one, depending on di bigger than 0 or di equal to 0. But in the first case, you also need the condition omega I theta check equals to 1. So only if that condition holds, then you have the conjecture as stated, and you don't need the correction term. So the correction term is rather complicated, so I won't show it here, but it will be in the paper that's going to be posted soon. So when does this condition hold? So this obviously has to do with minuscule cominuscule, so it will hold in all these cases. So in type ADE, it holds for all the minuscule nodes. In type BN, it holds for the cominuscule and the minuscule nodes. But in type CN, it actually holds for all nodes. And here only I equals 1 is minuscule and cominuscule. And also we have some additional nodes which are not minuscule or cominuscule. It's the node 4 in type F4 and the first node in type G2 using the standard labeling on the Dingin diagram, like for instance in Humphrey's book. So we have a couple more cases where it holds as stated beside the minuscule and the cominuscule nodes. And these are all governed by this condition. And actually, there is more combinatorics coming in here. There is a piecewise linear path version of the quantum alcove model known as quantum Buch-Mihalcea paths, which are in some sense easier to use for dealing with these special cases. But I won't get into that. The essence of the proof is the one I showed you before. So then applications of this conjecture that's now proved in full generality. So recently, not so long ago, these people showed that if this conjecture is true for the type A flag variety, which now we know is true, it implies a presentation for the quantum K-theory of the flag variety, which is different than the one I've showed you here. In some sense, it's more natural because it's the ideal is given by deformations of the classical K-theoretic Whitney relations. But this Whitney presentation was also recently proved by different methods by this person. And now we open another avenue for once we know this quantum equals classical result, we open another avenue for deriving cancellation-free Chevalley formulas for partial flag manifolds for their quantum K-theory, because we know these 3-point invariants which lead to the calculation of the structure constants. So this is an alternative approach to the one we considered previously via Kato's map from G mod B to G mod P. So we want to see if this gives us some extra mileage for getting such cancellation-free formulas beside the ones that we already derived or not. And of course, it would be nice to find some geometric interpretation of this correction term in the conjectured quantum equals classical formula. And looking ahead, just a couple of things in this world that would be nice to do in the future. So we, beside the Chevalley formula, with Maeno in 2006, we also conjectured in type A, just for type A flag manifold, complete flag manifold, we conjectured a Peary formula. So a Peary formula is a formula with multiplication by a class indexed not by a simple reflection, but by a certain increasing or decreasing cycle. So products of consecutive simple reflections in an increasing or decreasing way. And this formula in the non-equivariant case was actually proved by Naito and Sagaki. It's already published this year. So it would be nice to do a T-equivariant version of this Pierre formula, which would now involve the quantum double Grothendieck polynomials, which were also shown to represent Schubert classes in T-equivariant quantum K-theory. Then also recently, these people gave a combinatorial formula for the quantum Schubert polynomials, which represent Schubert classes in quantum cohomology. And they use a version of the recently introduced bumpless pipe dreams, a quantum version of them. So they gave a combinatorial formula. It's not cancellation free, but it's nice to have a combinatorial formula because these polynomials were only defined with this quantization map. So there is no explicit formula. So it would be nice to have such a pipe dream formula for the quantum Grothendieck polynomials or for the double ones. And then there is this K-Peterson map in type A, which would be nice to understand better. So there was a lot of progress in this direction. Ikeda Iwao Naito, Ikeda Iwao Naito Yamaguchi, very recently. Also developed connections with the relativistic total lattice. Very interesting connections between quantum Grothendieck polynomials and these K-theoretic Catalan functions introduced by Blasiak, Morse, and Seelinger. Again, interesting connections between various bases, how they correspond through this K-Peterson isomorphism. And then we also would like to see how the various multiplication formulas that we have for quantum K-theory or K-theory of the semi-infinite flag manifold or the K-theory of the Efraim-Grassmannian, how the various multiplication formulas correspond. Can one tell something about the other world? So lots to do there. And finally, of course, much more to do in other types because a lot of work has just been done in type A. So I'll end here. Thank you very much.
Questions? What was that quantum bumpless pipe dream? Can you give us a brief description?
No, and I'm to be honest, I didn't look very much in detail related to them. Well, if you know the usual pipe dreams, there are some variations on them. And it's still a mystery to me how they guessed that formula. They basically showed that their formula satisfies a recurrence relation for the quantum Schubert polynomials, which is known as the transition formula. And transition formula basically comes from the Chevalley formula. So, but they really guessed that formula, or I don't know how they found it, but once they found it, they showed that it satisfied this transition formula. So hopefully we can probably do something similar for quantum Grothendieck polynomials, but it would be very hard to guess a pipe dream formula.
The situation is similar. If you have a guess, it's check that the
You're
guess.
right. Yeah, if we have a good guess, then I think using the Chevalley formula we can prove that it's correct. But I discussed this with specialists in pipe dreams and bumpless pipe dreams, and they said the K-theory case is much harder than the cohomology case. And even in the cohomology case, it's not a cancellation-free formula. So it's not the ideal thing.
AI people will love this. Easy to check once you have a guess.
Yeah, maybe AI can guess a formula, yeah.
So So you had one of your corollaries was like a Borel style presentation for quantum K theory of the type A flag manifold, because you had this mod out by elementary symmetrics.
Right.
So do you expect that same presentation, like a co-invariant style presentation for quantum K for other types as well? Or, I mean, that seems to be a result that was surprising
Right.
type A to me.
Yes, I think I would expect something similar in other types, and I know there are some people working on other types. I don't know exactly, maybe Leonardo or somebody else knows who is working on other presentations for other types.
It's supposed to be a total lattice type presentation all the time.
Right.
But maybe there are some difficulties in quantum cohomology. The type switch. So if the total lattice for the Lagrange dual corresponds to quantum cohomology for the actual space. Quantum cohomology of G mod B is given by the integrals of motion in the total lattice of G dual. And it's supposed to, something like that is supposed to work in all types, I don't know. In type A, that's the presentation that you get. There is another presentation, which is Whitney presentation, that is, I'm not sure how much type independence you can find. But do you have any hope for multiplications with exterior powers of tautological bundles?
Exterior powers of tautological bundles. No, but I guess yeah, that's a good thing to look for. Yeah, so right, so in general type we just have the Chevalley formula, and in type A we have the Peary formula, multiplication with these classes indexed by increasing decreasing cycles. Yeah, but no, I don't know anything else, but it would be interesting.
Okay, there are no more questions. Let's thank Cristian one more time.
Thank you very much.